Hi, this is David Delmas from Airbus, and I'm going to talk about our work on static analysis of Endian portability. This is joint work with Abdelraouf Wadjaout and Antoine Minet. A word on Endian at first. There's no consensus on the representation of a multi-byte scalar value in computer memory. Little Endian systems store the least significant byte at the lowest address, while big Endian systems do the opposite. Little Endian's systems include Intel processors, while Big Endian's include Internet protocols and legacy processors such as SMARC. Note that such a conflict might raise religious wars, such as the civil war Gulliver witnessed when traveling to the land of Lilliput, where Little Indians insisted that eggs should be broken at the little end and fought Big Indians who wanted to do the opposite. Now, Endian is an important source of portability bugs, especially for low-level C programs. Indeed, the C standard leaves the precise encoding of scalar values partly unspecified. As a consequence, the same source code might behave differently on platforms of opposite Endian. Hence, porting existing software to a new platform with opposite Endian can be quite challenging. Let us show this on an example. Here we have a program which reads a 2-byte integer from the network. This program is originally designed for a big Endian machine, so it reads the bytes into the bytes of X and copies X to Y, and then reads Y using the big Endian convention. Now, what happens if we run the same program on Little Endian machine? Well, we get the same bytes, but when evaluating Y with the Little Endian convention, we get a different value. Now, if we want both programs to have the same behavior, we need to change the assignment here and replace it with a byte swap. So we byte swap the bytes of X into Y and read Y using the Little Endian convention and get the same result as with the Big Endian program. Now, if we merge the two versions of the program using conditional inclusion directives, we get a so-called Endian portable program. Note that there are other ways to byte swap X into Y, such as bitwise arithmetics. This is extensively discussed in the paper, but skipped in the talk. We want to do Endian portability analysis. A program is called Endian portable if two Endian-specific versions thereof compute the same outputs when run on the same inputs on their respective platforms. In this talk, we present a static analysis able to infer the Endian portability of large, real-world, low-level C programs. After the example, let us present the syntax and semantics of the language. We deal with so-called double programs, as we may have two versions of the same programs. Double programs are composed of double statements, which can be simple statements shared by both versions, or pairs of statements, the parallel sign here denoting syntactic difference, such as difference coming from conditional inclusion directives. Note that even when both programs share the same code, the semantics might be different. Simple statements are standard C-like statement, where we assume every left value to have been preprocessed to scalar dereferences. Scalar types include integers and pointers. Expressions support pointer arithmetics at the level of bytes and non-deterministic choice. There are also additional statements to express specification, such as the assert sync statement, which says that both program versions agree on the value of the expression. Now, to define the semantics of such double program, we simply lift simple program semantics. Simple memory states are standard stores from variables to values, and double memory states are pairs of such simple memory states. This represents the Little Endian memory, and this represents the Big Endian memory. Now, to define the transfer functions, we leverage previous work on patch analysis. Uh, the semantics for two different statements running in two different environments is just the pairing of the semantics of individual statements as computed in their respective environments. The case of test is a bit more involved. It uses the F filter here to distinguish between cases where both program versions agree on the value of the controlling expression or disagree. Uh, these cases are stable tests and they are standard. These cases are unstable tests. Here, we compose the little endian version of the then branch filtered by the condition with the big endian version of the else branch filtered by the negation of the condition. And that is the dual case. The semantic for assert sync statements simply filters away any double memory environments uh, where the evaluation of expression E might give different results in the little endian program and big endian program. In this case, an alarm is raised. This is not represented here for conciseness. Now, the semantics for further statement is defined by standard induction on the syntax, yet we still have to define how we read and write to memory. And for this, we need a memory model. At the most concrete level, each program version holds values for individual bytes. Yet we deal with C programs with multi-byte access to memory, and we want to compute numerical invariance, hence the need for scalar cells. In addition, we work with low-level C programs which tend to abuse the weak type system of C with unions and pointers to get byte-level access to the encoding of scalars, hence cells might overlap. We thus view memory as a dynamic collection of cells, which are synthetic scalar variables holding values for memory dereferences discovered during the analysis. More precisely, a cell is a tuple with a base variable, an offset, a scalar type, an Endian S encoding, and a side, little endian program or big endian program. With this memory model and any standard numerical domain, we may define a static analysis using one dimension per cell. Let us do it on the example. This is the little endian memory, this is the big endian memory. When writing the same values to the bytes of X in both memories, we synthesize 1-byte cells for X in both memories and record equalities. Then we byte swap X into Y in the big endian memory, which synthesizes these cells. Then we read X in the big endian memory, which synthesizes these cells with a value based on the values of overlapping cells. Then we assign X to Y, which synthesizes this cell, and then we read Y, which synthesizes this cell, as we already have this one. And then the question is, do we have equality? Well, equality can be proven from the program invariance and cell constraints that we have inferred. However, these invariants are quite complex and would require an expressive domain such as polyhedra. And this is not an option as we plan to scale to large programs. However, we notice that many invariants are equalities and many equalities are between the little endian and big endian versions of the same cells. And this is not a surprise as we expect that in a portable program, most multi-byte cells are going to hold equal values in both memories. Therefore, we optimize our memory model for this common case, and we do it by sharing cells in the memory environment. We want a single representations for two cells from different program versions, but at the same memory location and holding equal values. We thus define B cells to be either a cell or a pair of cells holding equal values, which we call shared B cells. Recall the analysis of the example with cells. We synthesized cells for Y1 and Y2 and then queried for equality with a lot of pressure on the numerical domain. Now, if we move on to B cells, we first merge the memory representation. Um, we create shared B cells whenever equal values are written to bytes of X. We put much less pressure on the numerical domain. And when reading Y, we do not immediately try to synthesize Y1. The memory domain first try to synthesize a shared B cell for Y1 and Y2 as a proof of equality. And to do this, it looks for a number of possible memory patterns, among which the following. It looks for an existing cell in the environment, which would be equal to both Y1 and Y2, and X2 is a candidate, as this is recorded. Now it looks for overlapping 1-byte cells of X2 and Y1, and queries for equalities. And as X2 and Y1 have opposite Endian encoding, these equalities are exactly these ones. Here, the success of B-cell synthesis relies on this abstract pattern matching and on a few equalities which can be inferred from simple symbolic propagation or a full equality domain. Now we have implemented our work with the MOPSA platform, which allows for the development of precise static analysis of multiple languages for multiple properties. Our prototype is 3,000 lines of OCaml, most of which for the memory domain, and it leverages much more lines of the platform. We have benchmarked our prototype on open source and industrial software. We have chosen open source software projects available on GitHub with multiple patches related to Endian portability bugs. We analyze small slices using our specification primitives, and we are able to find all Endian portability bugs and to prove Endian portability where applicable. We also analyzed two large components of an avionics application developed at Airbus. This application is designed to run on an embedded big Endian processor. Nonetheless, these two components are designed to be portable to Little Endian, as they are to be reused as part of a simulator, which runs on an Intel processor. We analyzed these large code bases quite precisely with no false alarms related to Endian portability. Note that the analysis of module A was performed before it was integrated into the simulator. And all findings have been incorporated into the development cycles. As a result, the simulation team were faced with zero Endian portability issues when integrating module A into their simulators for the first time. To conclude, we have presented a static analysis of Endian portability based on a novel concrete collecting semantics, which relates the behaviors of two versions of a program running on platforms with different Endian-S. It is based on the joint memory abstractions, which infers relations between little and big Endian memories. We have developed a prototype static analyzer able to scale to large industrial software with zero false alarms. In the paper, we also present a symbolic predicate domain we use to infer relations between individual bytes of variables in the two programs, such as those established by bitwise arithmetics. For future work, we plan to industrialize this analysis to address avionics certification objectives related to simulation fidelity. We also plan to extend our analysis to further portability properties, such as portability between different layouts of C types or sizes of machine integers. And we also plan to analyze software patches modifying data structures where we think our B-cell approach should be successful. Thank you for your attention.